very good afternoon, everyone. I'm Shubhangi Rao and I'm working as an assistant professor at MLR Institute of Technology. And here I'm taking the subject electromagnetic field for second year AAA students. So today we are going to discuss about vector multiplication. So let's start. So what is vector multiplication and why it is needed? Vector multiplication's knowledge is required so that we can understand the transform of the vectors from one coordinate system to another coordinate system. And what are the types for that? First one is multiplication of a vector by a scalar, which is also called scalar multiplication, and it is given by C vector V. Another one is multiplication of one vector by a second vector. It is called as dot product, and it is also called scalar product, and it is given by vector A dot vector B, or in place of that vector X dot vector Y. So this is called dot product or scalar product. Third one is multiplication of one vector by second vector so as to produce another vector. That is called cross product, or it is also called vector product. It is given by vector A cross vector B. So what we understood is there are three types. We can do this vector multiplication. First one is multiplication of vector by scalar, another one which is called scalar multiplication, second one is dot product, and third one is vector product. So we will discuss these three types one by one. So first one is scalar product, which is also called dot product. So you can see the scalar or dot of two vector. You can take any vector like vector A and vector B. It will be denoted by vector A dot vector B, and it is defined as a product of magnitude of A, which is, you can call it as mod A, and mod of B. It is a product of the magnitude of A means mod A, and the magnitude of B is called mod B. So mod A, mod B, and the cosine of the angle between vector A and vector B. The small angle about which we are talking is this one, theta, right? So it can also be defined as the product of magnitude of A, B. It also can be defined as the product of magnitude of vector B and projection of A onto vector B, or it can be vice versa also. And how do we write it mathematically? It is written as vector A dot vector B is equals to mod of A, mod of B, cosine of the angle between A and B. So the result of such a dot product is scalar. That is why it is called scalar product. So this is your scalar product or dot product. There are some properties of dot product. While solving the problem, we must know these properties, so it will be helpful. So the first property is vector A dot vector B is equals to mod vector A mod vector V cosine of A B, where this theta AB is the smaller angle between A and B, right? Another property is A dot B is equals to 0. That means A is perpendicular to B. The third property is called commutative property, right? Which means if you write A dot B, it can be equal to B dot A. That is called commutative property. Fourth one is distributive property, means if you have three vectors A, B and vector C, and if you write it like A dot B plus C, so as per this property it can be written as vector A dot vector B plus vector A dot vector C. It's just like 2 into 3 plus 5, so it can be written as this A dot B plus A dot C. Next property is the dot product of the perpendicular unit vectors is 0. That means we know we have three vectors x, y and z. So if these three are perpendicular to each other, so when we take the dot product of the perpendicular units, means x will be parallel to y, y will be parallel to z. The fifth property is called the dot product of perpendicular unit vectors is 0. Means if you see, we have three vectors x, y and z. So x, y are perpendicular to each other, y, z are perpendicular to each other, and x and z is also perpendicular to each other. So when we write them in this form, ax dot ay will be equals to 0. Similarly, ay dot az will be equals to 0, because we know that y and z are perpendicular to each other. Similarly, z and x, they are also perpendicular to each other, so their dot product will be equals to 0. That is the fifth property. Next one is vector a dot vector a is equals to mod of vector a square. Seventh property is the same vector dot product will be equals to 1, means ax dot ax will be equals to 1, ay dot ay will be equals to 1, as well as az dot az will be equals to 1, right? For example, we have taken here for Cartesian coordinate system, if you have two vectors and you want to multiply it, a dot b, right? So a will be in Cartesian coordinate system will be ax plus ay plus az. Similarly, bx will be bx ax plus by ay plus bz az. So when we want to multiply them by using this dot product, it becomes ax bx, because ax dot ax here, when you write, for example, it can be written as ax ax plus ay plus az, and if we can see, the b is equals to bx ax plus by plus bz az. So if you want to multiply this a dot b, so how we are writing here, if you notice, ax bx, this and this, and here these two are also multiplied, ax dot ax, but we know by this property which we have seen in the point number 7, according to this property, ax dot ax will be equals to y. So this becomes ax bx. Then when we come to y component, it becomes ay by, and z component becomes az bz. So this is the example how we can use this property for the dot product of any two vectors, right? Apart from that, we can know the component of p in the direction of unit vector, right? So when we want to write it in such a manner, it becomes vector p dot vector a, right? Also, the component of p in the direction of q can be written as p dot aq, where aq is equals to vector q upon mod of vector q. So it becomes p dot vector q divided by mod of vector q. So these are some of the properties of dot product. Let us now discuss the applications of dot product. So first one is, we can determine the angle between two vectors. We already have seen a dot b is equals to mod of a mod of b cosine of the angle between a and b. So by using that particular formula, we can find out what is the angle, exact angle. For example, here this is a, this is b. So what is the value of this angle? So this can be found, right? So this is the first application. Second one is to find the component of a vector in a given direction. This also we have discussed just on the previous slide, right? If you see here, we have two vectors here. This is vector a, this is vector p. Now I want to see the vector, the component of vector p in the direction of unit vector a. So it can be written as vector p dot a. So when you elaborate it, it becomes mod of p mod of a cos theta, and hence it becomes mod of p cos theta, because basically this is the component in this particular direction, right? Fine. So let's move to next slide. Another application, we can also understand the work done by a constant force and can be expressed as a dot product of two vectors. For example, let us consider a constant force F which is acting on a body, right? And it is causing a displacement d. That is genuine when we are pushing a particular body. That means when we are applying a force on a body, it will cause some displacement. So that force is F and that displacement is d, right? Then surely some work is done. So that is given by W, right? So basically the work done W is the product of force and the component of displacement in the direction of force, and mathematically you can write it by using in this manner, by using this formula. So vector F d cos theta, which is nothing but the dot product of force and the displacement, right? Now, if this force is applied, it varies along the path, right? Then also by using the same formula, we can find out the total work done, which is to be calculated by integration of the dot product. Means this W is equals to F dot D, it can be written as integration. That means it will sum up the movement across all the paths. So by using this integration formula, we can write W is equals to integration of F dot dl, and here you can put some limit. From here to here, the work is done, right? So this is the third application of dot product, right? So that was about dot product. Next is vector product, which is also called cross product, right? So for dot product we have seen, which is also called scalar, it was A dot B. Cross product will be written by A cross B, vector A cross vector B, right? So this cross product can be given by, here we have given it by C, it can be taken something else also. So basically, what is cross product? So the cross product of any two vector, it says something about how perpendicular they are with each other, right? So when we write it in the form of formula, it becomes mod of C is equals to mod of A cross B, which is ultimately given by AB sine theta, right? If you see in this diagram, here we have taken this right hand thumb rule. So in this thumb rule, if you see, we have two vectors, this is A, this is B, and this third one, this thumb, is showing the cross product of vector A and vector B, right? By using this diagram also you can understand, right? This is A, this is B, and this is the cross product of A and B, and in the opposite direction it will give you the same magnitude. Here you have positive value and here you will have negative value, right? So by using cross product, we basically understand how perpendicular these two vectors are with each other, right? Now if you talk about this angle theta, it is the angle between the vectors, this angle. Another thing which we should know about the cross product is the cross product of any parallel vector will be is equals to 0, right? If they are parallel, obviously there is no angle between them, so ultimately it becomes 0. So cross product of any parallel vector is equals to 0, right? Another thing which we must know is cross product is maximum for perpendicular vectors, because we know the angle between them is 90. So the cross product would be maximum, right? So some few more things we can understand by taking the example of Cartesian coordinate system. Here we are using some Cartesian's unit vector I, j and k, and by using them we are understanding what will be the cross product of various components, right? So let us see I cross j, it becomes k, right? Like this, right? Or you can write it like this, right? So I cross j becomes k. Next is I cross k. Now this is not the sequence, right? But we know the magnitude will be j, right? But because we are changing the sequence, we are going in opposite direction, so it becomes minus j. Then j cross k, again same sequence, magnitude is I with positive sign, right? So this is with the different unit vectors. Now if we talk about the same unit vectors, so the cross product of the same unit vectors means if we talk about I cross I, it becomes j, 0. If we talk about j cross j, it becomes 0. If we talk about k cross k, again it becomes 0, right? We can elaborate it more by again using some more examples here, right? This is one of the property. What is A cross B, whether it is equals to B cross A or not. For this we have taken one example of this right hand thumb rule, right? So basically, right, by this you can understand, but in the palm you can take two vectors A and B. This thumb you can take as the resultant of both of them. Okay, so if you just go with this diagram, if you see, let us just place A and B where the one end is joined, means tail to tail. Okay, and the four fingers are pointed along with the first vector. Okay, let us now sweep from first vector A into the second vector with some small angle. Okay, and this outstretched thumb, it points the direction of C. Right, again whatever we have discussed in the first slide, I have just tried to explain it with the another example. Right, so basically this A cross B is equals to C. Now whether this A cross B is equals to B cross A or not, no, obviously A cross B will be equals to minus B cross A. Right, here also just like we have taken the example of right hand thumb rule, by using this right hand screw rule also the same concept can be understood. Right, here also we are moving the screw from A to B. Right, this is the plane of A to AB. Right, this is the screw, this is the AN. Right, when you want to write the cross product, again it becomes A cross B is equals to mod A mod B, sine of the angle between A and B, and AN is the unit vector, right, which is perpendicular to the plane of A and B. So this is the plane of AB and this is the AN, which is perpendicular to plane of A and B. Right, hope this is clear. Now we have some applications of cross product just like we had applications of dot product. So let us discuss them one by one. Right, so the cross product is the replacement to the right hand rule which is used in electrical engineering to determine the direction of force which is experienced by current carrying conductor which is placed in a magnetic field. So you can understand it by the example of a wire where the length is L and the current is I. So if the I is the current which is flowing through a conductor or a wire where the length of that wire is considered to be L, right, this. So this indicates the direction of current through the conductor. So the uniform magnetic flux density which is denoted by vector B, then the force experienced by the conductor will be given by F, which is equals to IL cross B, where B, as I just said, it is magnetic flux density, L is the length, I is the current which is flowing through the conductor, and the F is the force which is experienced by the conductor. Right, so this is one of the applications. Another application is the physical quantity which can be represented by the cross product is moment of the force. Right, the moment of a force which can also be called as a torque, maybe it is acting on a rigid body which can rotate about an axis which is perpendicular to the plane which is containing the force, is defined by the magnitude of the force which is multiplied by perpendicular distance. You consider this diagram, perpendicular distance from the force to axis. Right, this M is equals to R cross F will be given by mod of R mod of F, sine of the angle between both of them. Right, this one, and AN, where AN is the unit vector indicating the direction of M, right, which is perpendicular to this entire plane. Right, some properties are there, or you can call them applications also. Right, so A cross B is not equals to B cross A. We have already discussed it. A cross B will be equals to minus of B cross A. Right, another one is A cross B plus C, distributive property. Does it applicable here? So it becomes A cross B plus A cross C. Right, and for parallel vectors cross product will be 0. A cross A is equals to 0. Right, similarly if we take the unit vectors also, AX cross AX, AY cross AY and AZ cross AZ will be equals to 0. We have taken one example of this Cartesian system. So how we can write in this form? A cross B is equals to AX AY AZ and the components are AX BX, AY BY, AZ BZ. Right. Similarly, here we had 2 vectors. Similarly, here we can have 3 vectors also. A dot B cross C. So, how we can write it? AX, AY, AZ, BX, CX, BY, CY, BZ, CZ, like this. AX, BX, CX, AY, BY, CY, and AZ, BZ, CZ, right? Vector triple product. This is also one of the properties. A cross B cross C is equals to B A dot C minus C A dot B. BAC CAB rule it is called. Right. So again these properties are required for solving the problems. Right. Now we'll discuss about the transformation of vector, means from one coordinate system to another coordinate system. So here we are going to discuss about Cartesian to cylindrical. Cartesian means what will be the coordinates? It will be x, y, z. Cylindrical, r, phi, z, right? Where r is the radius of the cylinder, phi is the azimuthal angle which is measured from x-axis in anti-clockwise direction, and z is the height of the cylinder, right? Now we are going to elaborate this diagram. So if you see here we have, see this is the point, here we have taken the projection of this point and we have drawn, right, ax dot a phi, it becomes, because the angle, these are the magnitudes, this is cos 90 plus phi which is equals to minus sin phi. If you see ay dot ar, it becomes cos 90 minus theta because of the angle between ay and ar, so it becomes sin phi. A phi, it becomes cos phi, as the angle between both of them is also phi, right? If you see az dot ar, it is equals to az dot a phi. They both are equals to 0 because az is perpendicular to ar and a theta, right? And if you see az and az, because if they are like in the same direction, so it becomes 1, right? So we have these 1, 2, 3, 4, 5, 6, 7 points. By using them we can find out the angles, right? So this equation can be written as, for this transformation between Cartesian and cylindrical. For example, I want to write that Cartesian coordinate into the form of cylindrical. So AR, for example, let us take R, it becomes AX cos theta plus AY sin, not theta, phi. AX cos phi plus AY sin phi. Similarly, you can find A phi as A dot A phi and AZ can be written as A dot AZ, and here we get A phi is equals to minus AX sin phi plus AY cos phi. These all formulas we are writing by using these properties, and also AZ will be equals to AZ. That is common for both of them, both the systems, right? Next, now whatever we have discussed in the previous slides, this is written here in the form of table for x, y, z and for r, phi, z. So the angle between AX, AR we got as cos phi, between AX and A phi we got minus sin phi, between AX, AZ we got 0, between AY, AR we got sin phi, between AY, A phi we got cos phi, and between AY, AZ, as you see, whenever they are perpendicular we are getting 0 angle. Similarly, between AY, AZ and AR we are getting 0 because they are perpendicular. AZ, A phi 0. AZ, AZ because they are in the same direction, so we are getting 1, right? In this form also you can write the same table, right? So this was from Cartesian to cylindrical. Similarly, you can write it for cylindrical to Cartesian. So A is equals to AR plus A theta plus AZ, AZ, right? By using this, you can convert from Cartesian to cylindrical or cylindrical to Cartesian. Next is Cartesian to spherical, right? Cartesian means x, y, z and spherical means r, theta and phi, where r is the radius of the sphere, theta is the conical angle which is drawn from the z axis, right? And phi is the azimuthal angle again, right? So when you solve by using the same method which we have seen in the previous slide, this one. By using same concept, you can find the angles between AX AR, you will be getting sin theta cos phi. Between AX A theta, you will get cos theta cos phi. Between AX A phi, you will get minus sin phi. Between AY AR, you will be getting sin theta sin phi. Between AY and A theta, will get cos theta sin phi. And between AY A phi, we get cos phi. Between AZ AR, cos theta. Between AZ A phi, minus sin theta. And between AZ A phi, it's 0. And again, this table can be written here like this. So, Cartesian to spherical and spherical to Cartesian, this. Same angles, few differences, right? So, this was about the transformation of vector from Cartesian to spherical. That is all. This was about the vector product and the transformation. If you have any queries, you can write to us. Thank you very much.